The interviewer asks you to find the duplicate number in an array, but you can't use a hash table and you can't sort it. How do you do it? Hi everyone, I'm Rock. Don't forget to like, save, and subscribe, and let's dive into today's explanation. Let's first look at the problem requirements. You're given an array of length n plus 1, and all the numbers inside are in the range of 1 to noun. It's just like having 5 drawers but 6 apples. There's absolutely going to be at least one drawer with 2 apples in it. The problem explicitly tells us that only one number is duplicated, and our task is to catch it. Note that the number might appear multiple times. For example, in the first example given by the problem, the array has 5 numbers, 1, 3, 4, 2, and 2. The target value is obvious. You can tell at a glance that 2 is the duplicate, right? But the interviewer put 2 extremely strict constraints on you. First, you absolutely cannot modify the original array. Second, you can only use constant extra space. So here comes the question. When facing this problem, what's the most intuitive brute force solution? Many people might immediately think, I'll just sort the array, and any 2 adjacent identical numbers are the duplicates. Or, I'll set up a hash table, scan through it once, and instantly catch whoever appears twice. But sorting messes up the original array, and a hash table consumes extra space. These 2 moves are completely blocked by the interviewer's conditions. So where's the breakthrough? Here, we can cleverly transform the array into a linked list cycle detection problem. Pay attention here. The array indices go from 0 to n, while the numbers inside the array go from 1 to noun. We can treat the array index as the current node, and the value inside the array as the pointer to the next node. Because there are duplicate numbers, multiple nodes will definitely point to the exact same position, which inevitably forms a cycle. And that duplicate number is exactly the entrance to this cycle. Therefore, this problem is perfectly suited for the classic cycle-finding fast and slow pointers algorithm. Just talking about it might be a bit confusing, so let's picture it in our heads. Let's take the array we just mentioned, 1, 3, 4, 2, and 2. First, we start at the beginning, which is index 0. We place both our slow pointer, the slow tortoise, and our fast pointer, the fast hare, right here. Round 1. The slow tortoise takes 1 step. It looks at the value at index 0, which is 1, so it crawls over to index 1. The fast hare needs to take 2 steps. It follows the 1 at index 0 to run to index 1, then sees the value at index 1 is 3, and whoosh, dashes over to index 3. Now the tortoise is at 1, and the hare is at 3. Round 2. The tortoise crawls 1 step from 1, and based on the value 3 inside, arrives at index 3. The hare starts from 3 and takes 2 steps. Index 3 holds a 2, and index 2 holds a 4, so the hare stops at index 4. Now the tortoise is at 3, and the hare is at 4. Round 3. The tortoise crawls 1 step from 3 and arrives at index 2. The hare takes 2 steps from 4. Index 4 holds a 2, and index 2 holds a 4, so the hare goes right back to index 4. It just ran a lap in the cycle. Now the tortoise is at 2, and the hare is at 4. Round 4. The tortoise crawls 1 step from 2 and arrives at index 4. The hare takes 2 steps from 4, and just like before, ends up stopping at index 4. Look closely here, everyone. The tortoise and the hare have met at index 4. What does this mean? It means there is indeed a cycle in our linked list. Next comes the crucial step of finding the cycle entrance. We magically turn the hare into a new tortoise right where it is, and we pick it up and drop it back at the starting line, which is index 0. Now, both tortoises set off at the same time, each taking only 1 step at a time. Step 1. The new tortoise at the start goes to index 1, while the old tortoise goes from index 4 to index 2. Step 2. The new tortoise goes to index 3, and the old tortoise goes to index 4. Step 3. The new tortoise goes from index 3 to index 2, and the old tortoise goes from index 4 to index 2. Isn't that pretty amazing? Let's distill the picture we just painted into the core logical framework for our code. No matter what language you use, the core is just these 2 steps. Step 1 is finding the meeting point. We initialize 2 variables, a slow pointer and a fast pointer, both equal to 0. Then we start an infinite loop. The slow pointer updates to the value at its current position each time, which equals taking 1 step. The fast pointer updates to the value of the value at its current position, which is taking 2 steps. We keep checking inside the loop, and the moment the fast and slow pointers are equal, we break out of the loop. Step 2 is finding the entrance to the cycle. We define a new head pointer and initialize it to 0 as well. At this point, we let the head pointer and the slow pointer, which just stopped, move forward together, with both taking only 1 step at a time. We write a loop. As long as these 2 pointers aren't equal, they keep updating their positions based on the values. When they finally equal each other, the loop ends. We just return the value at this meeting point, and that is the duplicate number we are looking for. Finally, let's summarize the complexity of this problem. Because we're just making the pointers run laps in the array, the number of steps they run is proportional to the length of the array, so the time complexity is an excellent ON. And throughout this process, we only declared a few variables like the fast and slow pointers, without relying on any extra data structures, perfectly satisfying the strict O1 space complexity requirement. By cleverly mapping the array into a linked list, this seemingly clueless, highly restricted problem instantly turned into our familiar two-pointer cycle detection problem. Alright, that's it for today's problem. See you in the next episode. Bye-bye.